to join. So, good morning, good afternoon, good evening, everybody. Welcome to this week's EMinar. We'll wait a minute or two while people are coming in before I'll give the introduction. And in the meantime,
I see you're running an inversion in the background.
was preparation for an inversion. It wasn't quite running yet, but yes. Well, as you know, there's always another inversion to run.
There's always another inversion to run. That is true.
Okay, people are coming in. Okay, so this week's speaker is Anandaroop Ray, and he'll talk to us about Julia-based geophysical optimization and Bayesian inference. Before I talk a little bit more about this, as usual, I'll give a bit of an overview of what's happening and a short explanation for those of you who are here for the first time. As many of you know, you can find past and future EMinars on the MTNet page. You can see the URL here at the bottom, or you just type MTNet into Google, and you will see a list of the previous seasons. We're in season 3 now, with all the speakers and where they have made it available, and I think that's the case for about 90 or even 95% of the people. You can find YouTube links to previous presentations, so you can see everything that has been done, and you can, in many cases, also get the slides. And for those EMinars that are upcoming, you can register and get notifications so that you don't miss it in the future. Next week, we have Bob Lowe on the exploration history of the discovery of 2 VMS deposits beneath the Phanerozoic cover of the Flin-Flon. So that's at 10 o'clock Universal Time, so 12 o'clock in Central Europe. And then...
Sorry, Max, that's a mistake. It's at 1400 UT.
1400, okay, yeah. So same time as today. We have 1400 UT now, yes? I think so. Yeah. And then there are 2 more scheduled EMinars in June, but more importantly, there are 2 open slots. So if somebody in this audience either wants to give an EMinar or knows of somebody who wants to give an EMinar, then please get in touch. We have still slots available on the 7th of June and, on the 21st of June. So send an email to Alan or any of me or any of the other EMinar organizers. And then on the 14th of June, we have Maxim Smirnov talking about deposit to regional scale exploration from the DREX project. And on the 28th of June is the last EMinar of the season, and that will be an open mic, so open discussion for up to 2 hours on anything you want to discuss about MT. And if you want to raise certain topics, you can do it on the day, but you can also send us an email beforehand that maybe we can prepare a bit. So, as I said, today Anandaroop is going to talk about Julia-based geophysical optimization and Bayesian inference. And he is a geophysicist using applied mathematics for exploration and resource management, and has worked in different capacities in industry and academia since 2007, and is now part of Geoscience Australia, where he's doing work on inversion techniques, and he will present some of that to us today. And I think with that, I'll stop sharing and hand over to you, Anand.
Sounds good, Max. Let me share my screen. You should be seeing the first slide now.
Yeah, still with the menus around it, so not full screen yet.
And how about
Now
that?
it's coming. Yep, that looks good.
Okay, so yeah, so mostly everything that I do, and a lot of our division at Geoscience Australia, which is Australia's federal geoscience agency, in the minerals, energy, and groundwater division. A lot of our work these days is funded by the Exploring for the Future program. And so that's what all of this work falls under. Enough of the advertising now. Let's get on to what we've been doing. I feel like today's topic is a bit of a monster. There's a bit of software engineering, there's a bit of optimization, there's Bayesian inference, there's trying to put it all together. And I cannot think of a more appropriate host than Max Morecamp to be alongside me today for this. So I've tried to put a bunch of things together, but really it's the distillation of ideas from various people, and you can see that list, and I've got a ... at the end because that list just seems to get bigger, and seems like the amount I know keeps getting smaller. But anyway, with that now, let us begin and get to the first slide. So everything that I'm going to show you today is done using the Julia language. That's a language that has come out of MIT as part of someone's PhD thesis, would you believe it, about 10 years ago now. And it has really done very well for itself. And for a bunch of reasons, it has become very popular in the world of numerical modeling. So the package that I have written primarily, it's mostly me with the help of a few other colleagues, particularly Richard Taylor, who now works at Q Control. So we've written this package called HiQGA, which is very imaginatively named High Quality Geophysical Analysis, and it's also got the GA there. Get it? Geoscience Australia. So this very cleverly named package, and we can do a whole bunch of stuff. My day job is mostly as an airborne electromagnetic geophysicist. And so one of the reasons why I was able to convince our management that we need to do this is because we need a next generation of airborne electromagnetic imaging codes, because a lot of the stuff was written back in the 80s and 90s and early 2000s, and there's a whole cascade of retirements going to happen very soon. So we've sort of thought about this being a capability maintenance or capability development program as well. But everything we do is open source. So you're welcome to use it, to commercialize it, to add to it. Just credit us, because even though it's free software, it's not free. Someone has to pay for my salary. I have to put in the time to write this. So the first thing you should probably do is install Julia. You can do that by going to this URL here. And then you can after you've installed Julia, just add it from the Julia package manager as the instructions here say. Now, there's a bunch of ways you can look at the examples that are on the website. You can go to the highlighted URL, you can hit the code box, and you can download the package as a zip. Or you can, do your command line commando business, and you can clone it with Git, which is what I personally prefer. Because I'm not a commando in real life, at least I can be one at the keyboard. So when I think of inference or optimization, especially inference, this is what I think of. This used to be one of my favorite webcomics. I used to visit XKCD quite regularly as a graduate student. Haven't been doing that more recently. I don't know why. I think they're still going, but this is a particularly good one. So there's this thing you want to know about. That's in my case, the Earth's subsurface. And that's really hard to observe. So we study the proxy variable and, it's just like airborne electromagnetic data or control source EM data or magnetotelluric data. Or, if you're a seismologist, it's seismic waves, etc. So, this is this is what we get to observe. And we hope through the physics that somehow it is connected in some intrinsic way to what we want to find out about, which is the Earth. So this cartoon should explain everything, and I don't have to say any more now. I can go home. No, I'm kidding. I'm already at home. So jumping straight into it, how would you fit, this bunch of points over here? So I've got, some bunch of sampled points along the x-axis. The x-axis is your given. There's no error in the x-axis, and there are some values y or f of x. I'm assuming it's some function of x. And, there's some error bars. These errors seem to be homoscedastic. They don't have to be. But yeah, so, if you had to fit the set of data, how would you do it? You've got 39 data points, and you've got, it seems, something like 65 observation points or something. There's no right answer, but one way of doing this you could think of is you could represent this in matrix form. So you could think of a mapping from the observables f of x to the points on the x-axis. So say there are 65 such points. If you had all the data, instead of having just 39 data, if you had all the data, you could do this one-to-one mapping, and you could write this in matrix form, matrix vector form. However, we don't have all the data. So say you only had the second data point. You can write this as a vector dot product. So you've got this row vector, which has a 1 in the column representing the particular datum that you have, and you've got all the x's. And that row vector, a funky way to write that is by writing E2. So if you had 3 data points, say, so you have the 2nd, 4th, and the 9th, this is how you'd write it. So you have 3 row vectors there, and you have all the x's. So if you did this, you still have to find all the x's, and I've just told you that there's some 65 of them, but you've only got 35 observations or so, and you can write this mapping, the A matrix, I have now shown you as an image, but it's sort of beginning to take shape. It's beginning to take a familiar linear problem in the linear algebra sense form. And you'll be like, okay, we're doing linear inversion again. I know what's going on. And you can formulate an objective function phi. You can take the gradient of that with respect to x, find the stationary point by setting that equal to 0. And you do a little bit of math, you get the normal equations, and voila, you have, the least squares equation that every geophysicist knows and loves so much. But are we really done? So if I just plot up A transpose A, it's already in diagonal form. So you know that these are the eigenvalues. So there's only zeros, which are the black values, and the ones, which are the white values. And you can see that along the diagonal, you've got zeros. So you can't invert this. So you're not done. I lied. So then you'll say, I know what you're talking about. I'm going to put in a dampener. I'm going to do ridge regression. I'm going to put in this delta square, this very small positive number, and that's going to stabilize my matrix inversion. I won't have those pesky zeros anymore. And there's a whole bunch of reasons as to why you should do this. You should look up the theory of ridge regression. You'll get a certain bias, but it'll stabilize your results. It'll dampen your results towards 0. And you could get the ridge solution. And the ridge solution, if you ask me, is not such a great solution. I mean, it could be, but this doesn't look like a very reasonable solution if I connect the dots in this manner with the black lines. So the next thing I can do is I can enforce some form of smoothness. And over here, you've got an R operator. So this is a first differences operator. What it's basically doing is it's acting on your the thing you want to find out, which is the variable x, the vector x, and it's doing one subtraction and one addition from consecutive elements. So you've got, for reasons of mathematical convenience, I've got a 0 at the top row, but after that, it gives you x2 minus x1, x3 minus x2. So it's basically giving you differences between adjacent elements, which are ordered in a certain way spatially. So we could try to do something with these differences, as in we could try to keep these differences to a minimum. And one way of doing it, and if you're a Douglas Adams fan, you recognize what that cartoon there is. It is, we're basically saying, oh no, not again. How many times do I have to see this equation because I've studied it in undergrad or grad school, or when I picked up geophysical inverse theory or Menke's book? I never want to see this again. But don't worry, I'm showing you cartoons. There's only a few more equations to go, and then it's all pictures, I promise. So what you're doing over here is you've got an objective function now. And instead of just having the data term, y minus ax, and the 2 norm of that, you've also got this lambda square term, and you're trying to enforce that smoothness I talked about. So these 2 terms are traded off with this lambda square, and you've heard this before, but it never hurts to hear it again, and I reassure myself when I say it again as well. So if you wanted to pay more attention to the smoothness term, you would, of course, hike up this lambda square term. And if you kept increasing this lambda square term, and it's a positive quantity, if you made it infinite, well, the only way to then minimize this objective function is to keep the norm of Rx, that's this guy over there, equal to 0. And what that means is that you basically kept all the first differences, basically constant. So x2 minus x1, x3 minus x2, they're all 0. So that would just give you, a straight line or a plane or however you want to look at this in multiple dimensions. On the other hand, if you kept lambda square equal to 0, then you'd get back to the least square solution that I showed you earlier. But you wouldn't be able to get away with a pure least square solution because in this case, the eigenvalues are degenerate. But anyway, assuming that you wanted to maintain some smoothness using the first differences operator that I just showed you, with a very small positive value of lambda square, we can find what I'm going to call the maximum likelihood estimator, or MLE, smooth solution. And that MLE smooth solution is what you see in orange. And you'll notice that this is a lot better than the ridge solution, which was very, very spiky. And it's mostly hitting all the data points. And the data points are given in blue as before. But what you have is also the true model, or the true function value, and that true function value is given by the black line. And I'll tell you where I got the true values from. It's not arbitrary, it's not just something that I created. So you've got the maximum likelihood estimate, that's the orange model. You've got the true values that are given to you by the black line. And I'm also now showing you this thing known as the Occam model, which is the red line. And you'll see that the Occam model is even smoother than the maximum likelihood estimate, though in the maximum likelihood estimate model, we did enforce some measure of smoothness. I've also plotted for you here something called distance from the truth. So what essentially I've done is I've computed on the y-axis between every data point, that's the blue line, and the corresponding model. So if it's the Occam model, that's the distance between the blue points and the red line. And I've done that for every location on the x-axis. And I've squared them and I've summed them. And I've taken the square root, and that distance from the truth for Occam turns out to be 2.1. I can also do the same thing for the maximum likelihood estimate model. That is, I can take the values of the truth from the orange model and sorry, I just made a mistake. I just said that I was going to compute the distances from the blue to the model. It's always from the black to the red or from the black to the orange. So in the case of the maximum likelihood estimate, it's from the black to the orange. And for the Occam model, it's from the red to the black. And I can do this for every location on the x-axis. I can square it, I can sum it, and I'll get that distance from the truth. And that turns out to be 2.4 for the maximum likelihood smooth model. And it turns out to be 2.1 for the Occam model. So what you can see over here is that there's something remarkable happening, that even though I'm not trying to fit every single data point in blue, the Occam model is actually closer to the true model, which is the black model, than the maximum likelihood estimate model. So clearly, the data errors, so the y minus ax norm, is lower for the maximum likelihood model. However, the distance from the truth, that is the distance to the black line for the maximum likelihood model, is larger than it is for the Occam model. And the Occam model is smoother. So there's something very profound going on over here. And this is because the Occam model, and you can read the paper by Constable, and Parker from 1987, is, though it's not guaranteed, because there are no numerical guarantees of smoothness as far as I'm aware, it is the smoothest model within data noise that you've been able to find. And so it's quite remarkable, because this is actually coming from the natural world. We've got that black line actually coming from a well log. So if I were to place the x-axis at the depths at which they were recorded, this is actually coming from a well log in the Permian Basin. So it's envisioned on a well log in the Permian Basin. You've got log 10 resistivity on the y-axis, and on the x-axis you've got depth. So if I stretch this black line out to the right depths in the Earth, it's actually a resistivity log, that's from an induction log. So there's something profound about the Earth, and maybe a lesson about geology is that the Earth is a continuous beast. And we like to enforce smoothness when we can. And there are many notions of smoothness. It doesn't have to be a true norm, as I'm going to show you now. So if we look at the general nonlinear case, we have an objective function. I've got some data weights now. That's given to you by this matrix W. You can think of it as a matrix of standard deviations along the diagonal and zero everywhere else, or the inverse of the standard deviation. And we've got that within a 2 norm. And then we've got the smoothness norm that I told you about. But instead of having a 2 norm, I've got a more general P norm. However, for ease of differentiation and for showing you what it is we're trying to do, I'm going to set P equals 2, which is the usual case for many inversions. And we'll have this equation over here where we've got lambda square RM 2 norm square. And we proceed as before. How do we get the stationary point of this? Well, there's a bit of a trick. We don't derive directly with respect to the model M, which is what we want to find out. We derive with respect to a small change in M, or delta M. So after you do this linearization, you do this both for the forward operator as well as the regularization. But most importantly for the forward operator, this gives rise to this term known as the Jacobian. So that's the J matrix over here. So that's the number of data by the number of model parameters. And this is no different from just first order Taylor series expansions. So it just looks more complicated because it's multivariable calculus. Once you've done this, you can then go on and creep along. And I'm sorry, but I just keep making these pop culture references because that kind of helps me stay sane when I'm doing these derivations. And I also just enjoy it very much and subject you to this, this pain in my terrible sense of humor. There's a Radiohead song called Creep. So what we're doing is we're creeping along from a a given estimate, and then we find the increment by which to move, and so that's called creeping in Bob Parker's book on inverse theory. So we can write the residual as f of m minus d, and derive with respect to delta m, find the stationary point by setting equal to 0, and we then again have a linear problem to solve, the solution of which I have outlined in black for you. But I ask you to keep in mind a few things. The quantity to the right over here in brackets is the gradient, and the quantity in brackets to the left over here is the approximate Hessian. And this is important because everybody and their cousin is doing machine learning right now. And if I were to write it in this form, where I write the gradient, in this particular form with the nebula and the m phi, and I write eta to show you the approximate Hessian inverse, then I can write that m nu equals m wherever I started from, minus eta times the gradient. And this is just gradient descent. And the gradient is always pointing uphill, but we want to descend, which is why we've got this negative sign. And so this is really how you do gradient descent. So whether you're thinking of Newton's method, Gauss-Newton, steepest descent, they're all related and in not very different ways. The devil is in the details. But in general, what I've shown you here is basically some kind of Gauss-Newton method of doing gradient descent. So a nonlinear problem, if you were to do gradient descent, is basically successive linearization. And you continue doing this until you've hit some form of Mozarov discrepancy principle, which in our case is trying to find the smoothest model within data error. And in our particular case, in electromagnetic inversion, this is known as Occam's inversion. So what it is that we can directly go from gradient descent to Bayes' theorem. If you stay with me, if you followed me all this time, I promise you this is like the second last page of equations. So we can rewrite the objective function, which we had with the data weights W, which was like that, which I've boxed in red. And then we've got the objective function, which I've just expanded out a little bit. So I've just written that out as a dot product. And if I do that and I identify W transpose W as the inverse of the data covariance matrix, and I identify lambda square R transpose R as the inverse of the model covariance matrix, then, if you look at the second box in red, it begins to look familiar to those of you who are Bayesians. You've suddenly got this, oh, wait a second, that looks like a likelihood. And that looks like, what I put within a prior covariance. So it's beginning to look familiar to you now. So indeed, if I make these identifications of taking the objective function and adding a constant and putting a log before a particular probability, I can write log p of the data given the model as a negative half of this particular term. This is known as the negative log likelihood. And I can do something similar with this log p of m. And we can then, going from logs to exponentials, we can write the probability of the model given the data is proportional to the probability of the data given the model times the probability of the model. And all of you who are Bayesians are now jumping for joy and have stopped despairing about the fact that I went on and on about gradient descent. But really, what I just showed you was this. And I think this is best read from right to left, where you've got the prior, where M is a model that you have prior experience that tells you that it has certain characteristics that's independent of the data. So that's the prior probability encapsulated in PM. Then you've got the model likelihood that shows you how accurately you've been able to compute the data once you've examined the forward computation due to that model M against the data. That's known as the likelihood. It gives you the accuracy of your geophysical simulation. And then you put these two together, you're basically weighting one by the other. So you might have taught something about this particular model, and if it fits well, you will boost your prior belief, and that gives you the posterior belief. And if it does not fit so well, you will reduce your prior belief, and that again is the posterior belief. And I like to use the word belief here because really, you are making assumptions about the prior, right? As in, there is such a thing as having an inappropriate prior or an appropriate prior, and we can get into metaphysical discussions that I'll save for the end of the talk if we'd like to get there. But really, what it is that we're doing, if we think about it, whether it's from an optimization point of view, or whether it's from you know, a Bayesian sampling point of view, or whether you're sampling or not, it doesn't matter. Whether from a Bayesian point of view or from an optimization point of view, there is no objective, truthful, best inversion. You're always making choices. So there's no escaping this. So, you know, the determinists will tell you, oh, Bayesians are making up their priors, and it's true, they are. But if you look at gradient descent and optimization, in order to get a stable geophysical solution, you know, you do need to make choices. You need to select a data norm. You do need to select a model norm. You do need to select a regularizer. You do need to select a regularization operator. So there are choices to be made, no matter what you do. So really, I mean, I think it's much ado about nothing. But it is important to make sensible choices and to be aware of their consequences. And Andrew Valentine has been doing some really great work with Malcolm Sainsbury to talk about what these choices mean when you've made a particular choice of regularization operator. It's got a really good set of papers in the last few years. And again, Occam is one very good choice, but it's not the only one. So jumping straight into something less abstract, I promised you no more equations, and so they're gone. Here's an AEM inverse problem. So this is a fixed wing aircraft. And by the way, I know that was a bit of a slog. Am I still connected to people? Can they hear me? Can I get some acknowledgement of some sort? Yes. Excellent, excellent. Thank you, Max. Yes. Yeah, okay. It's a little bit disjointed speaking into a screen, especially in the dead of the night in Australia here. I don't want to be talking to myself. So this plane here is a fixed wing aircraft, and it is towing behind it a receiver bird. And this receiver bird is, you know, it's so I think the fixed wing aircraft moves at about 300 kilometers per hour. It's pretty fast. So the receiver bird is being towed behind it, and it's sort of moving like that. It's yawing, pitching, and rolling. And we're collecting data on X, Y, and Z component coils. And of primary importance, especially for layered Earth, are the X and Z component coils, not so much the Y. And what it is that you're always having to, you know, model in the frame of reference of the receiver. So it's not enough to model the Earth and the electromagnetic response of the stack of conductivity layers that you see over here. You also have to put this in the frame of the receiver. So you have to know the rotations and the rotation angles of the transmitter, which is a loop around the plane. And you've also got to know the rotation angles of the receiver. So thank you, Babak. Very encouraging. So yeah, so that's sort of what we're looking at. And if you look at this image over here, what we're doing is we're saying that, look, it doesn't matter what the pitch of our antenna assembly is, the receiver antenna assembly is, because in the XZ plane, the amplitude of the received B field will be the same, because it doesn't matter how the XZ plane is pitching. Within the XZ plane, the magnitude of the resultant vector remains the same irrespective of the pitch, right? So I've plotted, assuming that there is no yaw, I've plotted the magnitude of the secondary, actually this is the primary and secondary together, B field as a function of time. So this is a time domain electromagnetic inverse problem. So there's the data errors that you see in green over there. And so the inverse problem, of course, is to recover the conductivity of the Earth. And in this case, because it's a synthetic, we know what that is, but it's a good exercise to do. And we can do this from both a Bayesian point of view and a deterministic point of view. And if I show you the solutions, on the right here are the Bayesian as well as the Occam solutions. So the Bayesian solutions are distributions of conductivity with depth, the probabilities of which are given by color. So the hotter colors are more probable and the darker colors are less probable. You also have at every depth the 10th, 50th, and 90th percentiles of posterior conductivity. So between the P90 and the P10, you got 90 minus 10, or the 80% credible interval. And wherever the credible intervals are pinched, it means, or wherever you see this chicken neck, it means that there's a high concentration of probability mass in that region. The true model is also superimposed over there. So you see that where you've got a conductor, you've got a very high probability of imaging that correctly. And I've also plotted for you in yellow the Occam inversion model. So that's the smoothest deterministic inversion model that we were able to find. And we're getting into a little bit of the code over here. So if you go to our GitHub website and you download the entire repository, you'll find an examples folder. And the particular AEM system we're talking about is the Tempest AEM system. We've got gradient-based synthetics. They go as, you first make the model, you run the 0.1 file within Julia, you set a bunch of options in the 0.2 file, you run it in the 0.3 file, you also run it with geometry nuisances to see what the effect of not knowing the geometry parameters is in the 0.3 run inversion nuisance.jl. And then finally, to plot the results, you run the 0.4 file. Exactly in the same way, the 0.1 file is almost exactly similar, except in one, you switch on modeling of the Jacobian or not, because MCMC, at least the way we've done it, does not need the Jacobian. Again, you set a bunch of options, you run the AEM inversion file, 0.3.jl, you plot the results, and for both, there's this file called electronics high altitude.jl, which has some important characteristics to do with the source waveform, the receiver times, as well as the noise, because the noise is very important to calculate the likelihood. So I'm just gonna bring this here to see how I'm doing. Okay, so we're about 30 minutes in. So then we can also do interaction plots or cross plots between the various nuisances. So on this axis, we've got the height of the receiver above the ground, and we've got the transmitter receiver separation. And the dashed lines give you the bounds within which we can search for them. So you've got both the sampling results, the MCMC Bayesian inference sampling results in green, and you've also got the true values given to you by the plus or the vertical line. And with the red plus and the red vertical line, you've got the deterministic inversion results. And so you'll notice that, well, you get a distribution for the Bayesian results, and you get a single answer for the deterministic gradient Occam results. And notice how this is not a nice surface to be sort of navigating. Notice that, if you look at the histogram over here of ZRX, the true value, the black value, is adjacent to a very high probability region. But to the left, you've also got this low probability region. So it's a jagged surface. It's not very well connected. So it does make for difficult traversal of your misfit space. The inline separation between the transmitter and the receiver, you're extremely sensitive to. So that's a little bit easier to determine. And you can see that with the estimate as well. So again, if you don't bound your estimates of the geometry parameters, and by the geometry parameters, I mean the transmitter receiver horizontal separation and the receiver height, if you don't bound them properly, they will trade off with the conductivities that you have in the subsurface, and you will get incorrect results to do with those. And so it's quite important to keep track of them. So that's one way of looking at it. And from a mechanics point of view, you know, you've got the same physics operator. You've got this tempest operator, which I'm going to talk about in some detail in a few more slides. And you've got two different Julia methods. One is called gradient inversion, and the other one is called main. Because initially, when I started writing this code, I thought I'd only do, you know, Bayesian inference, because we had a stock standard gradient inversion code, and we didn't have one that could do nuisances for airborne electromagnetics. But just because Julia is so easy to code in, I was able to add the gradient inversion stuff afterwards. But yeah, I'll tell you a little more about how I did that in a few slides. But the important thing to take home is you have the same forward operator, the tempest operator. You supply it to different methods, and you can do MCMC, or you can do gradient descent. And one very important thing, I think, to think about is, you know, don't lose sight of what it is that your inversion is doing, because, you know, that lambda square that I told you about in Occam, it's, you know, it's, you have to do line searches, and you sort of have to backtrack a little bit, or you have to do root finding to be able to find the smoothest model. Sometimes that doesn't work. So the Hessian inverse is not good enough to give you the next step in the gradient direction. So you've got to reduce the step size by half. So there's a whole lot of tricks. So if you're able to, in your inversion itself, or within the framework that you're doing the inversion, also plot the results. Like, you know, I can see that at iteration 4, it's done 1, 2, 3, 4, 5, 6 tries in the line search. And it's terminated the line search at this point, because, you know, it's gotten a massive misfit decrease from the previous iteration. And you can see what the other models are doing in the line search. So we know, and I promised you, that the models will be smoother if lambda square is higher. So the smooth models are shown to you over here in the lighter colors. And the model to do with the chi-square of 66.51 that it's finally settled on is shown to you in red. And the true model is shown in black. So you can get an idea as to how you know, your inversion is doing, or whether you've coded things right within Julia itself. And that is just great. You can also look at, so this was in one iteration. These were the inner iterations. So you can look at the outer iterations of the Gauss-Newton, or Occam in this case, and you can see that it converged within 6 iterations. And I'm showing you the best model at every step. So this is just a great way to build your intuition about how you know, inversion works. And I sometimes marvel, like, you know, in the 1970s and 80s, when people first wrote inversion, they didn't have all of this. They didn't have Julia or MATLAB or any of these things. And I wonder how they built their intuition, really. But anyway, in this case, for the it's a 2-step alternating inversion. For the conductivities, we use a within bounds modification of Occam, so that your resistivities can never be outside certain values. And for the transmitter receiver geometry, you know, I gave up. I said, I'm not writing that myself. I used this BFGS code, which you can get from a Julia package known as Optim. And I think it does linear programming to be able to enforce a barrier to keep the nuisances, that is the transmitter receiver inline separation and the height of the receiver within bounds. And that's barrier BFGS. You can look up Nosedal and Wright to figure out how all that works. And I think this is probably my favorite slide. If I can't show you anything else and I leave you here, I'll be happy. You know, those operators, the regularization operators R that I wrote, they can be really large matrices. You have to construct them. So matrix construction takes a long time. Storing matrices is memory intensive. So sure, for a 65 layer model, it's not such a big deal. It's 65 times 65 times, you know, take the memory allocation of a double. However, if your models get larger, etc., it's really important to do matrix-free operator construction. And if you look at where my mouse is pointing here, I can say make a regularization operator for the Tempest operator, and it gives you a 65 by 65 linear map. But it's not really constructing it, because how I'm constructing it, I know that it's first differences. So there's very efficient ways to do first differences, which is just the diff operator. So that's kind of what you see over here. So you've got the, you know, to create the linear map, I've got the diff operator as well as its transpose. That's R transpose 1D operator. And these are the operations you need to create the transpose of the regularization operator. And then I can make a linear map like I show you over here. And then I can inspect it explicitly by forming the matrix. And I can form the matrix to do with that operator R. And look, I've got that 0 in the first row as I promised. I have -1, 1, -1, 1, etc., right down to -1, 1 in the last row. Now, I can also construct a second differences regularization operator by cascading the operators. So I can make R operate on R, and then I can find the full matrix again. And then this is what it looks like. And now you begin to see central differences, 1, -2, 1, sorry, second differences. And so, yeah, you can just go to town with this. And it gives you a very nice framework for being able to do your math. It looks like math, it reads like math, it's memory efficient. And here we have, you know, my creeping step or the Newton step. I've got J transpose W, and I've got a comma to give you W times the residual. And look at how I'm writing it. I'm saying the Jacobian of the operator F, it's F dot J transpose times F dot W. So that's J transpose W. And I've got, you know, W times the residual from the operator. But look at how I write the Hessian. I write it as J transpose W times J transpose W transpose plus lambda square R transpose R plus something else. But look at how I derive the math. I told you this is the approximate Hessian. So you've got J transpose W transpose WJ. That's exactly what I've written over here. I've got a lambda square R transpose R. What a lambda square R transpose R. I've also got some additional terms over here because I'm enforcing a prejudice, a background model. But this is beautiful because I've written the code to follow the math that I've derived. So it looks elegant. It makes for faster coding because I am writing as I think. And you see this guy here over here, that's I, that's the identity matrix. And it automatically knows how to fill in an identity matrix that is of the right dimensions to do with, you know, J transpose WJ plus lambda square R transpose R. It's all just beautiful. The math reads like, I mean, the code reads like the math that you've derived, and that just blows my mind. Another beautiful thing about this is you don't have to pay for expensive parallel programming licenses. You don't have to do any MPI-like parallelism because it's one-sided parallelism. From a manager, you need to set certain tasks to the worker processes, and the worker processes will report back as necessary. So we're doing parallel tempering over here. So I've got this function called swap temperatures. So temperatures in various chains. I'm doing a synchronized remote call. So you can think of this as an MPI send, but a synchronized send. But it's really just one task after the other being sent off. And because it's synchronized, you have to wait for the asynchronous tasks within that block to work. And you get the results of that using what is known as a remote call fetch. And what that remote call fetch is doing is it's saying, do MC step function at this particular process ID with this model, with these options, with these statistics, with these misfits, with this physics operator on this chain for this sample number. And this is a bunch of bookkeeping that I need to do. And then you do it for, the last iteration plus one to, the end of samples. And so it's just natively parallel, and it doesn't look as horrible as MPI code can sometimes. And it's also got distributed arrays, so that means that you don't have to do a whole lot of data movement. So it's really beautiful, the way this language has been thought out. So you might then say, well, all of this is great for your toy problem, but we've inverted 25,000 line kilometers of data, which is quite a test for my code. I've got to thank the New South Wales government as well as GA for letting me do this. This is in the state of New South Wales. This was carried out, I think, I should know, I spent a lot of time QCing the data and going to the field for this. I think this was before August of last year. So before August of last year, between May and August of last year, that this data was collected, 25,000 line kilometers of data. And this image, sorry, I haven't put a scale bar on. It's about 500 kilometers across the diagonal. What you're looking at is conductivity derived from airborne electromagnetics at 16 meters depth. This was collected using the SkyTem helicopter EM system, so which is different from the Tempest EM system, which I just showed you before. But it doesn't matter, because as long as you give it the right physics operator, you can use Occam, you can use MCMC, whatever you want to do. And if you zoom in, looking at this particular line over here, these are log 10 conductivities. Reds are conducting, blues are resistive. So what you see essentially over there is that there's been a lot of salt that's come into the system after a massive La Nina rainfall event last year. And then there's this area where, the water essentially is unfit for human consumption until it becomes more resistive down there. But zooming in to the southwest, if we look at what's going on at that one particular line, this is the deterministic conversion result. And it's really nice. You look at the northwest, you look at the southeast, and you look at your misfit along here. In most places, we've been able to fit the data. I can show you that 89% of the data have been fitted with a noise, 5% not so well, and 6% has not been fit. And that 6% that hasn't been fit is around here somewhere. But the rest of it has been fit well, just to make sure we're not imaging artifacts because of changes in the transmitter height. I've also plotted the transmitter height in this panel, the center panel, and the log 10 conductivities in Siemens per meter are plotted at the bottom. So you can see that the line started out in the southeast, and moved down moved up to the northwest, because 0 is to the right. So this is about a 30-kilometer long line. And it looks like, so first of all, when the interpreter saw this, they were very happy, because this is the kind of thing that they want to see. They've been waiting months for data collection. They haven't been able to go out in the field because of COVID, etc. So when they got this data and they could see this, they were like overjoyed. But they asked questions. What's going on over there? Is that, how many layers do you think we have over there? And so, they want to ask these questions, but we can answer with a little more certainty, because I can do the probabilistic inversions and I can plot the credible intervals. And you can see that the Occam model, which is given to you in yellow, that's sort of a profile down there, has 1, 2, 3 big conductors. So you get that 1, 2, 3. However, you've got to remember that the Occam model is an extremal model. It is the smoothest model that fits the data. However, there are other high probability models as well that can fit, especially when you're going toward the conducting side. So when you have cinching in the conducting end, like you do over here, you have good reason to believe that there could be another interface over there. So if we look at the deterministic section again, and I show you the percentiles of conductivity along the entire section, it lights up your imagination. So I'm showing you the 10th percentile here, the 50th percentile there, the 90th there. And this is far, far more interpretable when looking at percentiles. For example, what's going on over there? I mean, I have some layering to the east and I have some layering to the west, but in the middle, the layering sort of seems to disappear. It's not particularly geological, but we know the geology does not follow, you know, the layered earth to the west is not the layered earth to the east. So conductivities are changing, but the geology might not be, or I don't know if I'm saying that right, but all I'm trying to say is that you could still have the same layering geometry, but the conductivities will be changing laterally. And so you can see that in the 10th percentile. You can see that in the 90th percentile, and you sort of can see that in the 50th percentile as well. So now you're beginning to interpret things with a lot more confidence. You're beginning to look at other possibilities that are not extremal possibilities that are given to you by Occam. Occam is good, don't get me wrong. It's a good place to make a start. And I was quite skeptical of these results myself when I looked at them. But our geologists have well data in the area and they've pored over these things and they're like, no, these percentiles are good. We know that the whatever that sediment layer is underneath the Darling River, it continues in that area. So I believe them, and it kind of makes sense because this is not the only place where we see this. Now moving on to slightly more to the northwest a little bit. This is part of our flagship Oz AEM program, which at 20 kilometer spacing is close to a large part of the Australian continent. And so I've only shown you a particular swath of the Oz AEM acquisition there. And it's an important swath because it goes through Queensland, New South Wales, South Australia, and a little bit of the NT as well, just ending at the NT border. But that was the phase that I have inverted over here. These inversions were done by my colleague Yusen Lei Cooper, and this is using our flagship workhorse GALEI sounding by sounding Occam inversion, and it's great. You throw any electromagnetic data at it, it knows how to handle it, invert it, and you get this image of the subsurface. And this is a monumental piece of work in terms of the acquisition, because this has been done at this scale, at 20 kilometer line spacing with lines that are approximately 500 kilometers long. I think, you know, Australia is the only continent where we have as much coverage as we do. I'm only showing you something like 5% in this map, or 10%, whatever that is. But we're close to, you know, continental coverage at 20 kilometers. But what you see in these inversion results is, you know, you see these near surface conductors, you see some structure, but it all goes back to blue, and it is informative. You see some anticlines, and you see some synclines, and you see some paleovalleys, but we could perhaps do better. So just for your information, we're going down to about 350 meters depth. It's about 40x vertical exaggeration. But if you look at the P10, that's the 10th percentile model that I've inverted using HiKey-GA, the high probability conductors stand out. And I'll show you this in some more detail again, but just contrast this and that. You got a lot more information here, and I'll show you how. Now, if we look at the median model, that's really not so different from the Occam model, and we know this from what we've seen in the past. And if we look at the P90 section over here, then the high probability resistors stand out. And I'll show you this in some detail again. Now, if we bring in the Landsat imagery, look at the conducting end in the P10. This is the P10 section I'm showing you now. I've shown you this before. I've got the Landsat imagery in the background, and I'm going to outline for you some conductors. Look at how the reds are basically lining up with this waterway. So in the P10 section, which means the 10th percentile, if you've got reds and reds are conducting, it basically means that 90% of your probability mass is at the conducting end because you're at the red side. Conversely, if I go to the P90 section, what's happening now is that if I see blues in the section, it means that 90% of probability mass is now at the resistive end. And I'm going to show you some resistors now. And this is courtesy my colleague Neil Symington, who was extremely excited to see these things. You can see these blues really beginning to line up in the sections. So this is allowing you to do, probabilistic interpretation, and they're excited out of their minds when they see these things. You can also identify ambiguous structure. So for example, over here, this is a 500-kilometer long line. You see in the deterministic inversion, what could be one incised paleo valley, another incised paleo valley. You see these dips from the east and the west. However, you know that this is going back to a reference model. If you look at the probabilistic percentiles now, this is the 10th percentile. You're like, wait a second. This is beginning to look like something different. You look at the median section, you're like, this is certainly something different. And then you look at the 90th percentile, you're like, oh, that's definitely a resistor in there. And this looks more like a synclinal paleo valley. And again, just to show off how much HPC we've been doing, one line, if we decimate it every 48 soundings or so, roughly every 500 meters, one 500-kilometer line has about 1,000 soundings, which we can invert in using parallel tricks with 8320 CPUs in about 4.5 hours with the geometries. And we can simultaneously invert 5 such lines because that's the kind of compute we have at the ANU's National Computational Infrastructure. So this is just great. I mean, we've gone from prototypes to real data to using 41,600 CPUs for 4.5 hours at a time. So this just tells you not about how good of a programmer I am, but how much you can do with Julia. And you can use different geophysics for the same Julia interface. And some of you might know about surface magnetic resonance imaging. We've written this code, or my friend and former colleague Richard Taylor has. It's called SMERP inversion. It's a glue between HiQGA and SMR forward, which gives you the magnetic resonance imaging of the subsurface. Essentially what it is that we use the Earth's main field to give you a gyromagnetic, through the gyromagnetic ratio, a resonant frequency at which to pulse the Earth. And if you pulse the Earth at those frequencies, perpendicular to the Earth's inducing field, you'll have water molecules or hydrogen molecules, if they're present, they will then begin to get perturbed in the direction of the resonant field, and then they'll precess. And as you relax the field, the precession will go back to the direction of the Earth's magnetic field. And because you can think of protons as basically loops of current, when those loops of current are moving and changing, they lead to an EMF, which we can pick up at the surface. And so the signal strength corresponds to the amount of water. And that's basically how an MRI machine works. But we can't take the superconducting magnet out into the field, which is why we use the Earth's main field. And it's a very clever setup, but it's an inverse problem. We sort of need to figure out from the EMF that we've received at the surface, what the Earth's water saturation looks like. And we've also got a gamma ray log in this particular place, also in the Appendelling floodplains. And here is the vendor stock standard inversion, which is done with some kind of Moore Penrose pseudo inverse because it's a linear inversion. But again, it goes back to some reference model of zero at depth. But we know from the gamma log that the gamma is going to a very small value, which means it's likely to be sandy. But our inversion is pretty much matching the vendor's inversion at the shallower depths, but at deeper depths, supported by the gamma. We're saying, look, we know that there is at least an 8% probability of water saturation given over there. So what you have on the x-axis is water saturation, and on the y-axis, depth. So again, same Julia interface. So this is made possible by using subtypes in Julia that I've shown to you in red. So if you look at the code for doing MCMC sampling of the SMR stuff. The operator is known as sounding. If I look at the type of sounding, it says SMRP inversion.smr sounding known. Known means you assume that the data noise is known. If you look at the type of sounding, it tells you it is a trans-DGP operator. Similarly, so the top bunch of plots was to do with surface magnetic resonance. This bottom bunch of plots is to do with airborne electromagnetics. You use the AEM operator. The same Julia high-QGA MCMC method called main. But over here, if I say, what is the type of AEM? It says it's a trans-DGP skytime inversion del B Z over del T type of operator. So it's proportional to the voltage received at the receiver. What is the type of that again? Is it a subtype of a trans-DGP operator? It says true. So as long as you've got the right, as long as you can supply a misfit function to do with the operator type, the MCMC is happy to go. So I see that I'm coming close to an hour over here, so I'll begin to wrap up. What it is that under the hood, the MCMC works with Gaussian processes. And Gaussian processes have been studied for a long time. They're a fancy name for Kriging, but they've been studied by the machine learning fraternity quite carefully over the last many years. With the same equation that you see over here, this mu star equals k star inverse, km inverse m, with these kernels for k, which are basically matrices full of similarities between different points in your model domain. You can come up with functional representations for all kinds of things. It's basically a non-parametric regression. But my interest in this is that using a bunch of Gaussian process nuclei, these purple points over here, I can represent a function in 1D using these nuclei in 2D. I can interpolate this entire field in the background in 2D. So that's actually a milk drop that I've solved as part of an inverse regression problem to sort of give you this image of. Or I can, slice through, some structure in 3D, again, using these points over here. So, maybe I've got 60 points, but it allows me to interpolate an entire, AT by AT by AT volume. So whether it's 1D, 2D, or 3D, it's all represented by these Gaussian process nuclei. And by adding and subtracting nuclei, we can do the traditional Bayesian trans-D or transdimensional Markov chain Monte Carlo, which most of you should be familiar with, or if you're not, please talk to me. I'm happy to talk to you about it. So what this means is that we can regress images. Don't worry, I don't expect you to know what these things are. There are a bunch of points with certain pixel values, but I'll tell you that there are 332 points from a given image. You can do exactly the same kind of inference that I did for the AEM inversion problem. And this is one model with 119 points. When I do the interpolation between the 119 points, that's what it looks like. This is the mean of very many models that have been sampled, and this is the original. And this is kind of cool, as in, this is a 76,000 pixel image from which I only had 332 images, and I've been able to reconstruct a mean like that. So, it's not bad. It's using this entire trans-D Gaussian process MCMC, which underlies all the Bayesian inference that I've shown you, whether it be 1D or 2D. So for example, what you saw over here, there's a whole bunch of models that are interpolated to give you saturation models, the histograms of which you're seeing over here. Similarly, when you were looking, sorry about that, yeah, here, there's a whole bunch of resistivity nodes which are interpolated to give you resistivity models, which are then histogrammed to give you these plots. So yeah, so whether it's 1D or 2D or whether it's three-dimensional, the inference engine doesn't really care. And that's the nice thing about what you're seeing over here. And there's some fancy things you can do, because when you're talking about Gaussian processes, you need to give length scales. So then you can begin to go a little bit, like you can think of diving into the matrix. You can chain one second layer of inference to your first layer, where the first layer basically contains your model properties. In this case, pixel values. And your second layer contains the length scales that parameterize those pixel values. And I've got these two papers that you can sort of look up in some detail. But the point to take home is that with 200 to 300 Gaussian process nuclei across two layers, you can really compress, images. And if you can represent an image field, what that means is you can represent any 2D model field. And so you can do MT inversion with this, for example, which we have done, but we've done that with a one-layer parameterization. I'd love to do it with a two-layer parameterization. So this is the Mare 2D inversion of the Gemini salt field from Kerry Key's PhD thesis. This is the median model from the from Dan Blatter's PhD thesis, and this is the interquartile range, and you can really you're looking for a very resistive body, which is not the easiest of things to image with MT, because salts are extremely resistive. But yet, in the interquartile range, you're definitely able to see the salt body. You can see the overhangs, and this is a really nice piece of work, because you're not limited to the extremal models given to you by Occam. You're not limited to the smoothest models. So it's quite nice piece of work. And last but often ignored is the fact that we do all this great work, but we're not able to get it out to people because look, we're not software engineers. We it's cognitive overload to know gradient descent, then to know Bayesian inference and sampling and Markov chain Monte Carlo. And then you've got to be your own software engineer as well, because software engineers have better things to do than to hang around geophysicists, because they're going to get jobs in the industry or at Google. So, but however, Julia is nice because you can do package management by making your changes. So in this case, I did some stuff for VTK visualization. So that's how I showed you those nice plots of AusAEM in ParaView. And I said, hey, Julia robot, it's called Julia Registrator, register. And I actually did this evening. So this 4 hours ago should read 6 hours ago right now. And then the robot replies saying, oh, this is a pull request that you've made to the Julia hub, Julia registries for the Julia package universe. And if it is merged properly, you can create this tag and you can create a new version. And so what you have to do is you have to follow this link, see if it's been merged, and it's almost all automatic. And if it doesn't work, it tells you why it doesn't work. If you're registering a package for the first time, it takes up to a day. But if you're registering any new upgrades, it takes like only minutes. And then after you've done that, your users can basically just do from within the Julia prompt, update HiQGA, and they'll get the next version. So it's just brilliant. You don't have to worry about make files and messing around with dependencies, because it's all automatically managed, downloaded from the internet. So I know this is a bit of a wordy slide, but there's just so many things to say. Just focus on the highlighted bits. So Occam inversion models have low entropy. So when you're doing probabilistic inversion, your priors should generally encourage low entropy and some form of smoothness, and they should be adaptable. So if they're not smooth, they should then be able to adapt to show you the fact that they're not. If you've got Bayesian posteriors, then, as I showed you for the AusAEM example, you can do probabilistic assessment of geology, and that rapidly lets you screen for conductors and resistors. So yeah, sure, you spend a lot of time in the and compute, not even that much time, compute in getting the posterior conductivities or posterior distributions of whatever it is you're interested in. But then have at it. Spend your time on the interpretation, and don't worry about fast compute, because compute is becoming so much cheaper these days. So we've got this inversion framework with these ideas. That's the GitHub link. Julia has this type and subtype hierarchy, and this idea known as multiple dispatch, with which, whether you've got an optimizer or an MCMC sampler, as long as you give it a misfit function, or you give it a misfit function that can return a Jacobian, it just knows to send it to the right method for the right physics. One very important thing to keep in mind is that Julia reads like interpreted languages, but it is just in time compiled, and it is fast. And I encourage you to look at these benchmarks of that website there. There's a whole lot of excellent math libraries available: the fastest Fourier transform in the West, interpolations, Bessel, making meshes, whatever you want. The code reads like mathematics, and that's just so much easier to follow than trying to, write something in some vague loop somewhere with symbols that don't really make any sense. And, earlier I used to spend, at least during my PhD, I'd go to some high-level language, do some prototyping, then I'd have to scale it up and make it fast in C++ or Fortran, use BLAS and LAPACK. Then I'd have to bolt on MPI on top of that, maybe do some OpenMP as well, and then I'd get some results, and then I'd have to visualize things in Python or some high-level language again. I'm not going to name any trademarks, but you can do it all in Julia. You can do the visualization as well in Julia. And if you want to go to 3D, there's nice open source libraries like VTK and ParaView that you can use. Something that has massively increased my productivity is I don't have to deal with makefiles anymore, and I don't miss it. I really don't miss messing with makefiles and making clever makefiles that only update certain parts of my code when I change it. Because if it takes too long to compile a large bit of code, it's just, my eyes glaze and I go to sleep. So finally, I would say that, whether you're doing R&D, whether you're, in industry, or whether you're a student, it seems almost too good to be true. But, I've been using Julia now since 2016, because in my previous workplace, I sort of was very, very highly encouraged to use Julia, and I protested, and kicking and screaming, I started using it. But I find that it's excellent now for prototyping, for production work, and for package distribution, which is where the majority of us geophysicists sort of fall over, because it's not easy to distribute your package. How do you get people to know about it? But it's part of the Julia package registry if you are able to satisfy a few very simple requirements. And I've got to say, there's some continuous integration stuff that my colleague Richard Taylor did for me, for which I'm eternally grateful to him. I'm so sad that he left Geoscience Australia, but he's at a better place in his career. We'd love you to get involved, because this is an open source software project. So, we welcome your contributions. Feel free to send me an email, open a pull request, make all these issues, use the code, and I'm sure it's going to break, because at the present moment, I am the main developer and I've written like 98% of the code. So it works for me whenever I'm making changes somewhere. I don't have 100%, unit test coverage. So I don't know what I'm breaking when I make changes. So I encourage you to just use it and give me your feedback. And I will leave it there. Thank you.
Thank you. Thanks for that interesting talk. Certainly a lot was covered there, from computation to interpretation, and how to deal with software development. Certainly something many of us have to contend with. There is already one question on the chat. Maybe I'll sort of use my privilege as moderator and ask one first. I find your Well, first of all, I find your idea with the 10 percentile, that's really interesting. I mean, as you said, it really brings out those significant conductors or the 90 percentiles, yes, the significance resistors.
Yes.
Now, one question I have about those inversions, do you apply any lateral continuity between those different, I assume, 1D inversions?
That's the thing, as in it is amazing, but we don't. There is no lateral continuity applied. We can. That makes the inverse problem a little more complicated because now you've got to do matrix inversions for a larger model. But
yeah.
We really found that it doesn't add to our ability to interpret things. And very often what it does, it can sometimes join together artifacts. So, we sort of leave it as it is. And if I can go back to my slides, you see that there really isn't a lack of continuity. You can sort of see that, whether it's the 10th percentile, 50th percentile, 90th percentile, or even in the deterministic inversion, there's no lateral correlation applied. But, given the fact that, when the aircraft moves from one location to the next, and we've got a sounding every 10 meters or so, because it's a diffusion problem, you're probably smearing geology as you're acquiring soundings as well. So, applying lateral correlation, do it, but it's probably overkill and not necessary.
Yeah, and I agree that you have a very nice lateral continuity. And as you said, for probably every sort of location where that might improve things slightly, it will also make things worse in other places where you might have a fault or might have artifacts and they get smeared out. So yeah, it's always sort of a trade-off, right, between
yes,
different things. Okay, so one anonymous attendee asks, any tips on applying your Julia package to joint inversions like MT and airborne EM?
That is a very good question, and I sort of prepared for it, but I didn't have time to put in the slide. But what I'll do is I actually have a module that does that, I think, if I'm not mistaken. I do have a module that does that, but basically what it is, you've got to provide, oh, there it is, generic joint inversion. So you see, let me increase the font size there. So you've basically got to create, some operator, and there's some example code as well in the examples directories. But what you're basically doing for physics operator in a vector of physics operators, it just adds the misfit within a loop. So it just adds the negative log likelihood and it gives you back the summed negative log likelihood. And this is really how simple it is to do joint inversion of any two types of data, whether it be CSEM and MT in the marine environment or MT and AEM. I've even got some examples of doing MT and AEM in the examples folder, but I have to say that I'd advise proceeding with caution because remember, MT is, at a very simple level, pure TE mode, and it's a whole lot of frequencies. And time domain EM is also pure TE mode, and it's the superposition of results at each frequency, right? So, your mileage will vary, is what I'm saying about doing joint MT and AEM inversion. In cases where you don't have good information in the MT, frequency band, only in those cases, I think, will you get significant uplift from doing joint inversions. Otherwise, they're not complementary sensitivities, even in the shallow sections.
Yeah. And I think that's a general thing with joint inversion, right? You need to think carefully about like the complementarity of the sensitivities.
Yes.
Then there's Vikas Baranwal saying, thanks a lot for a nice presentation and going through all the details. Have you already added utilities for frequency domain helicopter EM?
Very good question. Now, we have not used frequency domain helicopter EM for a bit at Geoscience Australia. but there is no reason why it can't be done, because the time domain code is based on a frequency domain code. I mean, so you compute your frequencies at a whole bunch, you compute your Earth response at a whole bunch of frequencies, and then you Fourier transform these to time. So you just don't do the Fourier transform. So the mechanics of it is already there. It's just that I haven't got a specific wrapper to do it. But what we do have, as you can probably see on my screen, AEM, let's see, I should have something where if we go to the sources, you'll see AEM, VMD, HMD. So all of this stuff is basically in the frequency domain. I know it looks horrible over here, but you know, you're getting the field at a bunch of frequencies first. And so for I frequency, and enumerate frequencies at a whole bunch of wave numbers, et cetera, et cetera. So, you know, it's there. It's just that immediately after this, what we do is we get the field in the time domain, because most of the systems we use are in the time domain. But fundamentally, you know, whether it's controlled source electromagnetics or AEM, it's done first in the frequency domain, and then it's Fourier transform to time, at least for a layered Earth. If you're doing finite elements or finite differences or finite volumes, you can do different things. But from the modeling point of view, I don't have complicated modeling routines in what I'm doing. But we have used carry keys Mare 2D EM, which is not part of HiKeyGA, to do frequency domain CSEM inversion, which again, it's not time domain, it's not AEM, but you could, I suspect, repurpose it to do that. But that would have to be 2.5D or something like that. But if you just wanted to keep to 1D, you'd have to, you basically have to write a little bit of a wrapper using AEM, VMD, HMD, as you see over here.
Yeah, so another question from maybe the same, maybe a different anonymous attendee. For the deterministic inversion for the least squares regularization equation you showed, what is the implementation difference using SciPy, minimize, and Julia?
Oh, this is a very good question, and it's you know, this is something I keep getting asked very often. And I think, Max, you know, you'd probably agree, because, you know, you'd also, you know, get asked such a question. So line searches and stuff are where these things are different. Regularization operators are where these things are different. I have not used SciPy.minimize, but from what I understand, they give you generic packages for doing, you know, Newton's method, or, you know, steepest descent, and other such methods, and they will work. But, you know, how do you do something like Occam, where you basically, I think I have the line search here, where you sweep across, you know, the lambda square, and then you select the particular model that, you know, so say I had hit the data noise, that is the dashed line that you see over there, and you'd crossed it, then you've got to do root finding to come back. I don't think SciPy.minimize has these kinds of line searches. They have other line searches, but they might not be as specialized to geophysics in the way that we've got the smoothest model within noise, or in terms of spatial regularization. You might not be able to put in certain kinds of regularization operators. So that's how it's different.
Yeah, and I mean, I suppose, you know, the minimization or the optimization you do, they are not core features of the Julia language as such, right? You either wrote sort of your own version, or you used a software package, and then it's always this trade-off between having maximum control, having something sort of generic like SciPy minimize that sort of works in 90% of the sort of standard situations. So if you want to do something quick, then you use that. But if you want full control, then you need to do your own, right?
Exactly. Like, for example, in the for the transmitter geometry, I use BFGS, and BFGS is, I could write my own BFGS, but really there's people who can probably write a better BFGS code than I can. And when it comes to the linear programming to keep things within barriers, I just gave up. I said, look, I'm not doing that. I'll just use there's a package called optim.jl, and I just interplexed it into my code. And so I have two steps. So I have the Occam conductivity inversion, which I wrote myself, but I had to do a within bounds modification as well, because if you just do a generic gradient descent, it's unconstrained optimization. So you could be anywhere in space with your models, and you don't want that. You want to be limited to a certain range of conductivity. So you have to make these modifications, which again, I'm not sure you can get with scipy.minimize. But for barrier BFGS, why write it yourself? As in, you've got the code there. So it is that trade-off. And so you don't have to reinvent the wheel. There's two advantages to doing it. One is, maybe you want a specific shape of wheel for whatever you're trying to do. And also you learn a lot more if you can do it yourself, and you'll have that control that Max was talking about.
Yes. There was one last question at the moment, actually, in the chat about the recording being made available. I assume you don't have a problem with that, Anand, given that you share your code and everything.
Yeah, absolutely.
Yeah. So that will be uploaded to YouTube within the next few hours. I mean, Alan is dealing with that, and usually he does it really, really fast. And he already replied. So there's a link now in the chat. But if you just Google EMinar on YouTube, you will also be able to find that. Yes, as I can see, there are no more open questions at the moment. I assume, if any more questions come up, you can get in touch with Anand either through GitHub. There must be your information, or just the email to find more about this.
Well, I think on my final slide, we usually have a contact me or something like that. That's just sort of good policy from GA. So yeah, you can just, it's my full name at ga.gov.au. So you can just.
Yes, and you can see the email address there, or, if you Google your name, I'm sure it will come up. So yeah, thanks again for this interesting EMinar. Next week, as I mentioned before, we have Bob Lowe on exploration of VMS deposits, so more application focused. And with that, I'd like to thank everybody for your attention, Anand, for giving this talk, and hope to see you again next week.
Right. Thanks a lot.
Bye-bye.
Bye-bye.